AI is starting to look less like a fixed stack of identical transformer blocks and more like a system that spends compute where it actually matters. One paper shows you can route tokens by complexity. Another says long context ability comes from how full attention is nudged to learn, and a third cuts width in the middle of the network without paying the usual penalty. The pattern is clear. Smarter allocation beats brute force scaling, and the details here are exactly what matter if you build or deploy models. Let's explore the first paper, Chiaroscuro Attention Spending Compute in the Dark. Chiaroscuro Attention, or Chiar-Former, proposes a 4-layer hybrid transformer that routes each token to DCT spectral mixing, RBF kernel mixing, or full self-attention using per token spectral entropy as a complexity signal. The key finding is routing collapse. Learned gates consistently reject RBF and converge to a DCT plus attention design, which is not a failure but a discovery of the minimal useful operator set. On Wikitext 103, that collapsed Chiar DCT plus ATTN variant reaches 36.54 validation perplexity versus 66.62 for a full attention baseline, a 45% improvement, while cutting attention flops by 62.5% and total compute from 1.88 to 1.11 GFlops. The model's operating regime is narrow. It excels on large, naturalistic text, matches a full attention baseline on IMDb within 1.24 percentage points, but underperforms on Wikitext, 2, and ListOps, where scarce data or exact symbolic rule following favor uniform attention. The paper's central contribution is a theoretically grounded routing rule, spectral entropy, derived from DCT energy concentration that turns operator selection into a token-wise compute allocation problem rather than a uniform transformer design. Let's explore the second paper, Rethinking the Role of Efficient Attention in Hybrid Architectures. This paper from Tsinghua University and OpenBMB argues that efficient attention in hybrid language models is not the direct source of long context capability. Instead, it acts as an optimization prior that changes how quickly full attention layers learn retrieval. Across 7 architectures, scaling law fits show validation. Loss is nearly unchanged by the efficient attention choice, but log-long PPL diverges strongly early in training and then converges as training budget increases, with SWA 2048 lagging most. Mechanistically, receptive field restriction and needle in a haystack probing show long-range information is carried mainly by full attention, not by sliding window or recurrent mixers such as lightning attention, Mamba, 2, and gated delta net. The paper names the resulting effect large window laziness. Large SWA windows reduce the gradient signal that pushes full attention to form retrieval heads, delaying long-range learning. A simple design fix, applying NOP only to full attention layers in a small window SWA hybrid, substantially improves long context performance while keeping short context quality nearly flat. At S5, short av stays at 41.32, while long bench rises to 19.46, and ruler at 32K reaches 46.98, compared with 41.31, 18.3, and 41.86 for the SWA 128 baseline. Let's explore the third paper, Variable Width Transformers. MIT and MIT IBM Watson AI Lab researchers introduce variable width transformers, or is greater than, is less than formers, a decoder-only architecture that breaks the standard assumption of constant hidden width across depth by using a times-shaped schedule, wide early layers, a narrow middle bottleneck, and wide late layers. The key implementation is parameter-free residual resizing, where truncated dimensions are carried forward through a fixed global residual stream and restored when width expands, avoiding learned projection bottlenecks. Across dense models from 200M to 2B parameters and a 3B total, 1B active MOE model, the variable width design consistently beats parameter-matched constant width baselines on language model loss, while also reducing average layer size, which translates to smaller KV cache and lower compute. At the 2B scale, loss drops from 2.75, 1 to 2.726. P-flop, S-days fall from 16.92 to 16.49, and average layer size falls from 1600 to 1426. Scaling curve fits suggests the same loss can be reached with 77.8% of the flops and 85.1% of the average layer width. On downstream LAM evaluation harness benchmarks, the 2B model improves average accuracy from 56.1 to 57.2, and lambda perplexity from 8.18 to 7.43, While the Mo variant improves Wikitext perplexity from 16.36 to 15.98, analyses show denser MLP activation use, higher residual stream entropy in middle layers, and less compression valley collapse than standard transformers. That's a wrap on today's AI paper highlights. Thanks for watching.